Okay, so good morning, good afternoon, and good evening. Hope you are all doing well and staying safe. I am Mariam Shreif, a senior petroleum engineering student at the Lebanese American University, and I'll be moderating today's session. So, on behalf of PioPetro, I want to welcome you all to the second session of our online course, an overview of multi-stage completions for hydraulic fracturing operations, which has been presented by a distinguished speaker, Engineer Adam Burton. So, without any delay, let me reintroduce Engineer Burton. So, Engineer Burton's career has been focused on the completion of shales and similar unconventional plays that require multi-stage hydraulic fracturing. In 2015, Engineer Burton started the Unconventional Oil and Gas Training (UOCT), a company specializing in training and consulting for unconventional multi-stage completions. The UOCT provides in-house and video-on-demand training courses and performs projects including market studies, due diligence, reports on specific tool segments, and other projects. He also remains an active instructor and participant in the industry. So please join me in welcoming Engineer Barton. So thank you for joining us this afternoon. And on a final note, if you have any question related to the technical content of the presentation, please feel free to drop it down in the Q&A section, and we will sure try to answer as many questions as possible. Now, hope you guys enjoy this session, and Engineer Barton, the mic is yours.
Thank you, Miriam. Hello again, everyone. Thanks for joining again for day two. Today we'll be talking about plug and perf. Before we get started, I do want to remind you about my website, uog.training. You can find my video blog and free training courses as well. It has additional materials that won't be covered in this class. And then also I have a huge favor to ask of you as well. If you enjoy this content, if it's something that you like, please do subscribe to my YouTube channel. So that's where my video blog is, where it's ran through. And once again, I add videos to it. There's some content on there that won't be in this course as well. All right, so we stopped Tuesday with the introduction of unconventional reservoirs on hydraulic fracturing. And we stopped with the discussion of what the three completion types have been most effective and most efficient in these types of plays. Today, we're going to be focusing on the one in the upper left-hand corner, plug and perf. So we're going to use plugs and perforations to isolate and divert our frac job. So we'll start with our well. We've already drilled our horizontal well in our targeted reservoir. And once we're finished drilling the well, we pull out a hole with our drill string. Then we're going to run casing into the well into the intended depth. So this is just going to be steel pipe that lines the well bore. And then once we get to the intended depth, we're going to cement it into place. And once we've done our cement job, we give it time to set up, we do our pressure testing, and then we can move our drilling rig off of location. Once we're ready to begin fracturing, we'll zoom into the toe here. Now, if you have this set up here where you just have a blank casing string and you've cemented it into place, you no longer have the ability to pump into your wellbore, into that target reservoir. So in this particular case here, you're going to have through tubing intervention with coiled tubing or tubing conveyed perforating to be able to go in and perforate the well. So you perforate the first stage, those perforations will penetrate through the casing, through the cement, and into the target reservoir. And then once you've perforated your first stage, pull out a hole with your coiled tubing or your workover rig, and then then you can begin your first stage frac job. Now, another alternative that's become very common, especially in the U.S., is instead of having these perforations where you had to have through tubing intervention, you would run a cementable pressure-activated frac sleeve at the toe of the well. So this would be made up directly to the casing. You would cement it into place just like you would the casing string. And then once you're ready to begin fracturing, you simply apply the right amount of pressure, that sleeve will shift open, and you can begin fracturing your first stage. So it eliminates that through tubing run to be able to access your first stage. Another somewhat common trend, an alternative to the cementable pressure activated frac sleeve, is a wet shoe. So when you hear someone referring to a wet shoe, there's a couple of different tool components that they'll run with it, but really what they're trying to do is they're trying to leave this cement here at the toe wet. So what they'll do is they'll put sugar water in it so that the cement won't harden, and then it's still in a liquid form, and you can, once you're ready to begin fracturing, you can push through that wet cement and into the target reservoir and begin your first stage frac job like that. Now, once you get past the first stage, it really doesn't matter if you've had to do through tubing perforation, the sleeve, or the wet shoe, because now you've fractured that first stage and you now have the ability to pump back into the wellbore through the previously fractured stage. So at this point, once you're done with the first stage, most operators switch to a wireline deployed assembly. Your assembly will consist, of course, of wireline. At the bottom of the assembly, you have your frac plug. Above that, you're going to have your setting tool, which will set the plug and then release from it. And then above that, you're going to have your perforating guns. Now, all of these are activated by electric signals that are sent through the wireline. So once you pump down to the intended depth, you'll send an electric signal through the wireline that'll activate your setting tool, set the frac plug, and once the frac plug is set, your setting tool releases from the plug, and you can move your wireline assembly up the wellbore. So you pull it up hole to the depth of your first perforation, send another electric signal through the wireline, and that'll fire your first set of perforation guns. Pull up hole to the depth of your second set of perforations, another electric signal will fire your second set of perforations. And then pull up hole to the depth of your third perforation, and another electric signal will fire your third set of perforation guns. So this technique is called cluster perforating. So in this example we're looking at here, we have 3 individual sets of perforating guns. So this is going to be a 3 cluster per stage setup. Now, 3 to 5 clusters per stage used to be common in most of these plays about 5 years ago. But within the last couple of years, it's actually pretty common to see more like 6 to 12 clusters per stage. And the reason you can do that is because the technology with the perforating guns has drastically improved. So the switches in them and everything else, you can individually fire perforation guns and essentially have an unlimited number of perforating guns. So the practical limitation with the guns is not going to be the perforations or the perforating guns themselves. It's going to be the length of the overall assembly. Because keep in mind, each time you add a perforation gun, you make that, or a perforation cluster, you're going to make that assembly longer and longer. So really, the limitation is not the electronics, it's not the perforating guns, it's going to be the length of the equipment at surface. Because keep in mind, you still have to be able to pick up that assembly at surface and get it into the wellbore with a crane. So if you make it too long, then you're not going to be able to pick up that assembly. So just to kind of give you a point of reference, at least currently, the most I've heard of an operator running perforation guns in one stage has been 20 clusters per stage in a single wireline run. And even that is still not that common. Like I said, it's still averaging between 6 to 12 per stage. Now, once you're finished perforating for that stage, you want to pull out a hole with your wireline. You will rig up your pressure pumping crew, and you begin fracturing that second stage. And after that, you're just going to repeat the process. You shut down the frac job after you're finished fracturing the second stage, run your wireline in the wellbore, set a plug to isolate from the second stage, perforate your third stage, pull out a hole with wireline, and then fracture your third stage. And then you just repeat that over and over again. So this process with the wireline run and shutting down pumping between each stage has always been the weak point of plug and perf, because you're having to shut down pressure pumping between each stage, run your wireline, set your plug, perforate, and then pull out a hole with your wireline. So obviously it'll depend on your depths, but if you're running with a pretty good crew, then typically the fastest you can do that is about 2 hours. So it'll take about 2 hours between each stage to set the plug, perforate, pull out of the wellbore. And once again, that's with a very good crew. So if you have a less experienced crew, if something goes wrong, it can be much more timely. Now, once you finish fracturing, with a traditional plug and perf, these are composite plugs. So you do have to go in and do a through tubing intervention to mill out the plugs. And then once you've milled out the plugs, you can put the well on production. Now, this is a setup here, a little bit different on the wellbore construction. It's not done very often anymore, but especially since I know a lot of international students are on this course, it's worth mentioning. Just about the time I'm ready to write this system off, there's no one doing it. There's a handful of Canadian operators in certain plays that do it. And then it wasn't too long ago, I talked to an operator in the US that had a specific application where they wanted to use open hole packers. So with this type of setup, you're going to use open hole packers to isolate the annulus rather than cement. So you're going to make up these open hole packers directly to the casing string. You'll space them out whatever distance that you want the stages to be, and that'll be how you place your stages. Now, just like with the cemented plug and perf, you're going to start at the toe of the well and then work your way back up. And, especially if there's some people that aren't familiar with horizontal wells, let's just clarify what toe and heel of the well means. So the well itself looks like a foot. So towards the end of the well, that's going to be the toe of the well. And at the curve of the well, that looks like a heel, like you would see on your foot. So that's going to be the heel of the well. Now, like I said, it's not used very often, but the application that the US operator that I saw recently do it, they were planning on doing cemented plug and perf, but during the drilling process, they started taking fluid losses. So they didn't believe that they could get cement to isolate the annulus, that it would just absorb into the formation. And so because of that application, they chose to do open hole plug and perf, so they didn't have to worry about the cement setting up in the formation. So there's always going to be applications where one product and one wellbore construction may be a little bit better than the other. Now with this setup, in most cases, the toe of the well is going to be pre-perforated casing. So you're not going to have to do any kind of through tubing intervention to get those perforations in the wellbore. So basically, as soon as you're done with your drilling process, you move your drilling rig off of location. And as soon as you're ready to begin fracturing, then you're just going to start pumping through this pre-perforated casing at the toe of the well. After that, the process is going to be virtually the same. The only difference is you're going to have to be sure that you place your perforations between the packers, because the open hole packers are now what's isolating rather than cement. So you don't have the full flexibility that you would have with cement. So you have to be sure that you place that plug and those perforations in the intended stage as you line them out with the open hole packers. So deploying the frac plugs, hands down, the most common way to do this is once you get past that first stage, the operators choose to go to a wireline pump down deployment, because you can pump through that previously fractured stage, you can put it on wireline and pump it down, and wireline is, depending on the market, it's relatively cheap and relatively quickly available. Now, it also can be set up to run on coil tubing or a workover rig as well. So if you're in a situation where maybe the wireline is just not available, this could be an option. And what you saw in the US and the Canadian market specifically is before the 2015 downturn, there were some operators that did coil tubing deployed plug and perf. Now, the reason they did that, though, is because they were in high pressure, high temperature applications, and those composite plugs were not modified for pump down assembly. So you had a much, much higher risk of presetting the plugs if you tried to pump them down on wireline. So in those applications, they chose to go with coil tubing. After the 2015 downturn, the high pressure, high temperature plays were just not economical. So you don't see a lot of plug and perf coil tubing deployed nowadays. But if the high pressure, high temperature plays come back into being economically viable, or certain applications international where maybe wireline is just not an option, the coil tubing or workover rig deployment is an option. So over the years, there have been several modifications to the composite plugs to make them more, to make them easier to pump down in horizontal wells. So when you're looking at the assembly, there's a couple of different things you have to look at that can be problematic and make it more difficult to pump the plugs down. And that's going to be the amount of fluid bypass that's around the plug and the assembly, and also the diameter of the plug in the assembly. So we all know that that force is equal to pressure times area. So the larger area that you have to pump against, the more force that you're going to translate into that assembly. And also, the larger the diameter, the less fluid bypass you'll have around that plug. So what service companies have done to modify it, they've done one of two things. They've either added what they pretty much call a pump down kit. Overall, it's a very simple tool. In a lot of cases, it's just a piece of rubber that increases the diameter, and it helps minimize the fluid bypass and give the larger surface area to pump against. The other option that a few service companies have done is to just increase the design or the diameter on the design of the plug itself. So the plug itself is a little bit larger diameter and helps to make it easier to pump down in horizontal wells. So if we look at the gun barrel view, I think it'll be a little bit more obvious as to why it helps. So if you don't have that pump down kit or that larger diameter, you've got the overall diameter that you're pumping against, and then you have a relatively large fluid bypass area between the casing and the frac assembly. But if you add that pump down kit or just a larger diameter plug, now you're starting to minimize the amount of fluid bypass and the flow path that fluid can get around the assembly, and you've also increased that pressure, that area that you can apply pressure against and translate into force. So there's two different types of frac plugs out there, or two that are the most common anyway. And the top one here is going to be the ball isolated frac plug. So if we look at a cutout view, it's hollow through the mandrel. So as soon as you set the plug, you don't have isolation. You actually have to pump a ball downhole. When it lands on the seat, that's when you have your isolation. The other type of plug at the bottom, if we look at a cutout of it, it's a self-isolating plug. So it already has a device inside the mandrel that will, as soon as you apply pressure against it, it's going to latch or seal off, and then it holds pressure. So with the self-isolating plug, as soon as you've set the plug, you now have isolation, but with the ball isolating, it does require that additional step of pumping the ball downhole. And let's look at a couple of scenarios with the self-isolating plug versus the ball isolating plug. So in the first scenario, we'll look at everything's going to go correct on the operations, no operational issues. And so we'll start with the self-isolating plug. So we pump it down the hole through the previously fractured stage. We send our electric signal through our wire line, set the plug, and then we can pull up with our wireline assembly. Now with this plug, we have, it's self-isolating. So as soon as we set the plug, we have isolation. So now we can pressure test, make sure that the plug is set. And then once we've done that, then we can send our electric signals and fire our perforation guns. Once we've fired our perforation guns, pull out a hole with wireline, and now you can begin fracturing that second stage immediately. Now, same scenario, but now with the ball isolated plug. We pump through the previously fractured stage. Once we get to the intended depth, electric signal sets the setting tool, sets the plug, and then your setting tool releases and you can pull away. Now, if we look at the cutout view here, we have a hollow mandrel through that plug, so we still are communicating with this previously fractured stage. So we do not have isolation right now, and we can't do a pressure test to make sure that that plug is set. So we have to assume that the plug is set, and then we go about our perforation operations. So we send our electric signals, fire all of our clusters of perforations, and then once we've done that, pull out a hole with the wire line. Now, before you start, as you start pumping for the second stage, you're going to lead in with you're going to drop a frac ball. And then once as you continue pumping, the ball will go down hole, it'll land on seat, isolate from the previously fractured stage, and force the fluid to divert out of the second stage perforations. But as we all know, not everything goes perfectly and as planned in the field. So let's look at another scenario where it doesn't go quite as smoothly. So in this scenario, we'll start again with the self-isolating plug, pump it down hole. Once we get to the intended depth, electric signal sets the plug, pull away with the wire line, and because it's the self-isolating plug, we can pressure test. So we go to fire our first set of perforation guns, but this time the perforation gun doesn't fire. So you have a misfire or the perforations didn't fire at all, and you have to pull out a hole with your wire line, but now you don't have any way to pump into the well bore. Because you've isolated with this composite plug, you can no longer pump through the previously fractured stage. So in this scenario, you're going to have to shut down your fracturing operation and bring in coil tubing or a workover rig to go in through tubing and perforate those, perforate that second stage so that you can resume your frac job. Just to kind of give you an idea, it really just depends on your area and when coil tubing is available. So 7-8 years ago, when I was in the Marcellus, the Northeast United States, in a dry gas play, it wasn't this particular issue, but we had an issue with the well, and we had to have through tubing intervention. And the quickest available coil tubing unit was 6 weeks out. So the operator had to shut down the frac job and had to move on to another location and then come back to it after the coil tubing unit fixed the problem. So from a logistics and a cost standpoint, that's not a good thing for operators to do, to shut down one job, relocate their entire frac crew, and then come back later. So it adds a lot more expense to it. Now, same scenario, but with the ball isolating plug, we pump it through the previously fractured stage. We get it to the intended depth, we set the plug, and then pull away with the wireline assembly. And now, because we still have that hollow mandrel, we're still communicating with that previously fractured stage. If we send our electric signal to our perforation gun and it doesn't fire, then we pull out a pole with our wireline, we redress the perforation guns, and we can still pump back into the well bore through the plug and then pump it down hole, do our perforating process as we intended, and then you can recover and fracture that second stage pretty quickly. So so that still gives you, with the ball isolating plug, because you don't have that instant isolation, that gives you the ability to re-enter the well bore, or at least to pump through the well bore, so that you can recover from that the perforation gun not firing quickly. Now, over the years, the perforation guns have really improved on the technology, so it doesn't happen as commonly anymore that the perforation guns don't fire at all. And also, because we have so many perforation guns in the well bore, like I mentioned earlier, 6 to 12 clusters, in a lot of cases, you should be able to get 1, maybe 2 perforation clusters to fire. So that gives you the ability to pump in the well bore. So it doesn't happen as often anymore, but there's also another scenario where the ball isolating plug comes into place, and that's with screen outs. So just to remind you, we talked about screen outs yesterday. That's when you've pumped too much sand, too much volume of sand all at once, and you can no longer pump into the well bore. It blocks off where you're trying to fracture and then backs up the well. Now, if that happens and you have the ball isolated plug, when you do flow back, you don't have to just flow back through this second stage here. You can flow back that ball off seat, and you can also contribute flow back through the previously fractured stage as well. So it still is the most common way to set up these plugs, the ball isolation plug, just because it's a relatively cheap and relatively cheap insurance policy. So if something does go wrong, it just gives you a few more options. So let's talk about the fluid distribution through the clusters. So we'll go back to the 3-cluster example. And when we're designing our hydraulic frac job, we assume that we're going to get even distribution through our clusters. So if our frac design is 90 barrels a minute through 3 clusters, that means our design is 30 barrels a minute per cluster. We're assuming that we get even distribution. Now, the reality is just because of friction losses alone, you won't have that even distribution. And so because that fluid has to travel, you have a path of least resistance towards the heel perforation here, because the fluid has less distance to travel, and then towards the toe, it has the most distance. So it's a path of most resistance at the toe. So just on friction alone, your frac job would look something like this. And now this is an extremely simple, as far as the fluid distribution, it's an extremely complicated subject, because you're talking about different rock properties in each perforation, different flow patterns, things like that. But this is just a really simple way to visualize what we're trying to do and what we're trying to overcome when we're talking about limited entry perforating. So we'll stick with, like I said, just a very simple example of just the friction loss. So how would we overcome that? That's where the technique called limited entry perforating comes into play. So now you can see what we've done is we've changed the number of holes between each perforation. So at the toe-most perforation, now we have 5 holes. In the middle, we have 4. And in the heel-most perforation, we have 3 perforation holes. So now what we've created with this is the toe-most perforation with the 5 holes now has the most flow area. So that's a path of least resistance from a flow area standpoint. And the heel-most perforation has 3 perforations in it. So now that's a path of most resistance from a fluid area standpoint or flow area standpoint. So the idea is you want to balance out how much energy it takes for the fluid to exit each set of perforations. And hopefully, if you do it correctly anyway, then you get your even fluid distribution back through your clusters. Now, like I said, that's the simple way to look at it. That's the simple way to understand what limited entry is. Just looking at the friction loss itself. The reality is it is a lot more complicated than that. And just because of the different rock properties, the heterogeneity of the formation, we'll use a 6 cluster example now. And what happens when your frac is distributing something like this because of your rock properties? It can be very difficult to try to do a limited entry strategy successfully with this scenario. And so that's where something that called diverters comes into play. So if you look at a lot of the U.S. operators' public statements, in a lot of cases when they start talking about adding clusters per stage, in a lot of cases they added diverters as well. They do reference diverters. And so once again, we're going to look at a very simplistic example of diverters just to give you an idea of what we're trying to accomplish. And the most simplistic way to do that is to assume that as we pump through these 6 clusters, only one of the clusters is taking the fluid and the proppant. So you're going to kind of treat that as a individual stage. So you're going to pump the fluid and proppant volume that you want for that individual perforation. And then you pump enough diverter to block off near wellbore. And it blocks off and you can no longer pump into that cluster there, and it forces the fluid to divert into another cluster. So you pump the amount of fluid and proppant that you want to pump out of that second cluster, and then you pump another diverter and block off near wellbore there, and then it diverts out of another cluster. And then you just repeat that process until you've done that for each stage. Then once you're finished fracturing that stage, there's a couple of different types of diverters. So they can be dissolving. They can dissolve in the frac fluid and the production fluid. And some of them you may have to go in and do a through tubing intervention to mill out or circulate out of the well. So like I said, that's the extremely simplistic way to design diverters and to look at diverter design. But what happens when we go back to this example here, where we know that we're not getting it out of a single perforation? And in most cases, I think it's safe to say we know it's not distributing through a single cluster. So what happens here if we run diverter? So if we run diverter and we block off the most dominant one, this one has already been fractured and receiving it. So now it's going to be more dominant than it was supposed to be. The other thing is we don't exactly control where the perforation's going. So what happens, or excuse me, the diverter is going. So what happens if the diverter goes into a non-dominant perforation and blocks it off? Now the dominant perforations are really going to be even more dominant. And you also have to be careful how much diverter you're pumping, because if you pump too much, then you'll block off your entire stage, and you essentially have created yourself a screen out where you're going to have to shut down, wait for the diverters to dissolve, or go in through tubing and remove them. So this is an article from the SBE magazine, JPT. It was a great article. It was 2017, I believe. And I highly recommend going back and reading it if you're curious about diverters, because it goes through 5 case histories. And if I recall correctly, all of the case histories were very different. If I recall correctly, 2 of them really didn't see any difference when they used diverters. 2 of them did see a production increase with diverters, and then 1 of them did have operational issues, including pumping too much diverter and blocking off all the perforations. So it's a very good read on diverters, and even goes into some of the best practices on designing diverter strategies. And just to kind of give you another idea how complicated it can be and how much it is, it's definitely as much of an art as it is a science right now. I talked to an operator that's working in the Eagle Ford a little while back, and the Eagle Ford is in South Texas in the United States. And what their strategy was with diverters is they did a test well, or a test pad where they did 10 individual wells, and they tried to estimate how many clusters were taking the fluid and proppant. And what they found is that they 40% of the clusters were taking almost all of the fluid and proppant. So what they did on the remaining wells on that field is they would pump 40% of the frac job, pump enough diverter to block off 40% of the perforations, and then they would pump the remaining 60% of the frac job. So it's definitely not as easy as we showed in the visualization, and it is still a work in progress. So why are we looking at diverters? Why are we looking at some of these strategies with limited entry and stuff? And really the reason is we can start improving efficiencies overall. Because if we look at, I mentioned earlier that it used to be 3 to 5 clusters. So if we look at a 3 cluster per stage well that was ran 5 years ago, and now we take a modern day design where you essentially double the size of that stage. So one stage is 6 clusters per well. Now you have fewer stages overall in the well. You can pump that diverter halfway through and hope that it diverts to the other half. And if you execute this properly, if it goes as designed, now you have a very different well. The top scenario being 50 stages with 3 clusters per stage and with 150 clusters overall. And the bottom scenario could be a 25 stage system with 6 clusters per stage and still have the equivalent 150 clusters. But now you have half the stages. So you have half the plugs and half the deployment time. And you won't necessarily have half of the mill out time of the plugs, but it will be easier to mill out 25 plugs versus 50 plugs. So you will see additional savings there. So with all this complication, why do we use cluster perforating to begin with? It is entirely possible to do single entry plug and perf. You go in, you fire a single set of clusters or a single perforation, fracture through it, set a plug, perforate a single cluster, fracture, plug and perforate, and repeat the process. Now the reason we do this, or that we don't do single entry perforation fracturing, is because of efficiency purposes. So let's look at an example here. This is from a prominent Permian operator. So this is from their Q1 of 2016 investor presentation. And in that presentation, they reported that they were doing 9,000 foot laterals, 150 foot per stage, and 30 foot cluster spacing. So we'll stop real quick and review the nomenclature. So the 150 foot per stage spacing is going to be 150 feet between each plug. And the 30 foot cluster spacing is going to be 30 feet between each individual perforation. So using this information that they reported, that means that they had 60 stages overall in the well with 5 clusters per stage. And that means they had 300 individual injection points, so 300 individual clusters. So if we assume 2 hours of downtime between stages so that we can shut down the frac job, run our plug, set it, perforate, and pull out a hole, then a 60 stage job would be 5 days of downtime just so you can run your wireline between all the stages there. If you tried to break that into 300 stages, you'd be looking at a 25-day non-productive time. So very, very significant amount of non-productive time just to run your wireline between stages. Now, the same operator in the same presentation reported that the newest completion system that they were trying was a 9,000-foot lateral, 100 feet per stage with 15-foot cluster spacing. So that means that they had 90 stages per well, 6 clusters per stage, which means it's 540 total injection points. So if we make that same 2-hour assumption to run the plug, set it, perforate, and pull out a hole, 90 individual stages would be 7.5 days of wireline time. 540 stages would be 45 days of downtime. And that's, of course, just assuming that everything goes correctly, and that's without counting the fracturing time. So fracturing would be very, very inefficient with single entry plug and perf. So let's stick with that 540 injection point example that we were just looking at. So they had 540 individual perforations in the well. There's a lot of different ways you can set that up. You can do 180 stages with 3 clusters per stage. So that's going to be 15 days of downtime. You could do 90 stages with 6 clusters per stage, 7.5 days of downtime. Or you could do 45 stages with 12 clusters per stage, and now you're down to about 3.75 days of downtime to run your wireline. So you, as you can see, it's a very significant difference. And in the top scenario, you have 180 frac plugs. The middle, you have 90 frac plugs, and the bottom, you're going to have 45 frac plugs. So overall cost can be significantly impacted as well. But that operator that was reporting this in 2016, they weren't doing one-off wells, so their overall process was a little bit more efficient than what we discussed, just because they were in pad drilling mode and they had switched to simultaneous fracturing operations. So what we're looking at here, this is 2 laterals of the well. So imagine you're standing at surface, you look directly down, you're looking at the well bore, and what we're looking at here on the screen are the laterals going out in front of your feet. So once you're in pad drilling mode and the wellheads are close enough together, operators in most cases switch to simultaneous fracturing operations. And what that allows them to do is they can be pumping on well A while running wireline operations or tow operations on well B, and then they can switch the services over, run wireline on well A while fracturing well B, and then switch them over again. Pump fluid on and proppant on well A while running wireline on well B, and then just continuously switch them back and forth until your frac job is done. Now, when the wells are close enough together, you can set up your frac crew in one position. You can set up a manifold where you just turn a valve to control whether the fluid is going to well A or well B. So you never have to shut down, you never have to remobilize your crew. And then with the wireline, you just set the crane in between the 2 wellheads and then lower the wireline assembly into well A or well B, whichever you're doing. So that helps you significantly reduce the downtime, because now you're never having wireline sitting completely idle while fracturing, or more importantly, you don't have fracturing sitting completely idle while you're running wireline. Now, a lot of cases you're going to hear this technique called a zipper frac. In my opinion, it's a slang terminology, just because I was introduced to the concept of zipper fracs back in probably 2009. And so this is an SPE paper here if you want to know more about a true zipper frac and simultaneous frac, because they're very different objectives. They're not focused on surface efficiency. They're actually focused on downhole subsurface efficiency, if you will. So with those techniques, they're actually trying to play on stress shadowing effects and get a better frac job. But in most cases, operators are not currently doing that. They're doing what I refer to as simultaneous fracturing operations to improve surface efficiency. So if you want to know more about those, check out this SPE paper 140507. Now, this can also be applied on a large scale, and in the U.S. it's pretty common now to have this applied on a large scale. So you can have a large number of wells. You can also bring out multiple frac crews, multiple wireline crews, and then you can really start improving your efficiency and maybe even eliminating it completely by switching over these services between multiple wells. So we've gotten very, very good at reducing the amount of downtime and the overall efficiency with plug and perf over the years. And it's to the point where at least some operators report publicly that they've optimized the process to the point where they actually have eliminated the non-productive time between stages. So one of the newer technologies that we'll look at is the disintegrating frac plug. So with this one, this is the same overall functionality as the ball activated or the ball isolated frac plug. So once you set it in the wellbore, you have that hollow mandrel. You don't have that isolation. So you can still pump through that plug, the previously fractured stage. And so you have to pump that ball down hole to get the isolation with this plug. Once it's on seat, exact same functionality, you pump your frac job. But the big difference here is after you've finished your frac job, both the ball and the plug will disintegrate from the well and the wellbore fluids and remove itself from the well. So that helps eliminate the mill out of the plugs after the well's been fractured. So instead of like composite plugs where you have to have that coil tubing or workover rig run to mill out, that saves additional time there. It makes it a completely interventionless system because you don't have to go in and mill out those plugs. And then after the plug disintegrates, there is a full production diameter as well. So with these types of plugs, there are two primary materials that are used. It can be a alloy, a disintegrating alloy, or a disintegrating plastic. Just to kind of give you an idea of the different of the two types. With the alloys, it's typically a magnesium activated or magnesium based alloy. So it'll dissolve based on the temperatures in the well and the salinity of the fluid, and very quickly with acid. It reacts very quickly with acid. So you have to know your temperatures and also the salinity content of your fluid with the dissolvable alloys to be sure that they dissolve properly. The other type of plug is the dissolvable plastics, and what those plugs are based on is mainly temperature in the well, and they have to be able to be in contact with fluid, which we know fluid is down there. So those plugs don't, if you look at the marketing material for those plugs, they brand them as fluid agnostic, meaning it doesn't matter what the fluid is touching it as long as the fluid is touching it. So those are really more temperature dependent. So as long as you have enough temperature, the plastics will dissolve in the well. And so with the dissolvable plugs, some operators are doing full well bores, but in most plays, especially oil plays, they actually are mostly ran as a hybrid system. So what they'll do is they'll run dissolvable plugs outside of the range of coil tubing, where they feel safe milling out with coil tubing, and then they run traditional composite plugs within the range of coil tubing that they feel like they can mill out safely and easily. So after the frac job is over, they would go in and mill out the composite plugs, and then over time, that would be the dissolvable plugs remove themselves from the toe of the well, and then that gives them the ability to have an interventionless system at the toe of the well. Like I said, the most common plays right now are, well, especially in the U.S., they are oil plays instead of gas plays. So in most cases in the oil plays, you will see this hybrid scenario. But just to kind of give you a good example of where I've seen operators running a full wellbore of dissolvable plugs is the Haynesville Shale in the U.S. So it is a dry gas play. And the interesting thing about it is that if you're milling out plugs, you have to be in an underbalanced scenario. So it's a lot more risky to put additional fluid on top of a gas well after you've fractured it. So they run the underbalanced scenario so that the formation doesn't continue taking fluid. And some of the plug mill outs can last a week rather than a couple of days. So in that scenario, I have seen some operators switch to full well bores of dissolvable plugs because they don't have to go in and do that underbalanced drilling, and it saves them a lot of time and money because of the difficulty milling out plugs in dry gas. So as you'll see, especially on the last day, there are a lot of different exceptions to all the rules. There's a lot of different applications, and you really have to look at your regional economics, your wellbore dynamics, and everything else to really choose the setup and the completion type that really would fit your well. Okay. So that's it for today's lesson. So we do have about 15 minutes left for Q&A. If anybody has submitted it, I believe Miriam did tell you, but if you have any questions, do be sure to submit them to the Q&A. And in the meantime, until next week when we join back, here's all my contact information.
Okay, so thank you for your time. Now we will begin by addressing the questions. Can you explain more about the fiber optic monitoring technology?
I didn't cover any fiber optics. Is that the only thing that it said?
Yes, I think it's out it's not related to the presentation. If you, we can skip it if it's not related that much.
Yeah, I didn't talk anything about fiber optics. If whoever asked the question can maybe get a little bit more specific on what you're wondering, I'll see if I can answer it. But let's pass on it for now and see if they clarify what they're.
I believe the student want to ask about the general idea, what we can benefit of having fiber optic completion or smart completion. Maybe he mean to understand from where we get the production, which class are producing, which class are not producing. So,
sorry, Ahmed, you something happened and I lost you on that last bit.
Okay, I believe maybe he mean explanation for the general idea of installing fiber optics or smart completion to understand from where we get the production, from which clusters producing, which clusters not producing, and monitoring these things. So if you can tell us like a general idea about the concept, maybe this will answer the question.
Okay, yeah, so I'll try to kind of give an general overview. So there's two primary types of fiber optics that are used. It's DAS and DTS. So that's distributed temperature, and DTS is distributed temperature sensing. DAS is distributed acoustic sensing. So if everything goes correctly with that, then what that allows you to do, and hands down the most common one I've seen has been the DTS, the distributed temperature sensing. So what that allows you to do is when you have the temperature, it allows you to view a couple of things. When you're pumping into the well, your frac fluid is colder than your downhole fluid because assuming, depending on which formation you're in, obviously, but typically formations are at least 150 degrees. So your frac fluid may be 90 degrees. So what that allows you to do during the frac job is to see if you distribute it through your clusters and see where the fluid is going on your sleeves. The downside to that is there is some room for interpretation there too. So it's not 100% accurate. You do have to kind of do some educated guesses, if you will, because you're only seeing a limited where you believe the fluid is going based on the temperature changes. So there can be some anomalies here and there that are kind of tough to explain. And then it's really the same thing on the production end. So you're monitoring, you're able to monitor fluid flow by temperature. So if you can see the temperature changes between stages and try to get an idea of the different how the different stages are producing. Now, probably the number one challenge with fiber optics is cost, and that is significantly improved since it was introduced about 10 years ago. So they're much cheaper to do now, but especially since 2015, oil prices just never recovered to where it was, and obviously it's taken a huge hit during the pandemic. So what you really have to weigh out with fiber optics is the cost up front for the well, and are you getting a significant enough data to make your production better? So that is one of the main things. And then of course you have different challenges as far as if you're doing plug and perf with fiber optics, obviously you don't want to perforate the fiber optic line and sever it. So there are certain things like that to take into account. From what I'm seeing right now, it's not common to have fiber optics on every well. It's more a test pad. So they'll run it on maybe 5 to 10 wells, see what they can see, and then they make the assumptions about the rest of that field based on what they see in that handful of wells.
Okay, great. Thank you. Now the second question is that what is the maximum number of wells that we can fracture at the same time?
I guess I'm not really fully understanding that question. What is the maximum number of wells we can fracture at the same time?
Okay, let me explain what he mean. He mean you explain what is zipper fracking,
Mm-hmm.
and you frack two wells at the same time. So is it possible to do zipper fracking for 3 wells or 4 wells or 5 wells at the same time? What should be the maximum number of wells that we can do zipper fracking for them at the same time?
I mean, theoretically, yeah, there's not necessarily a max. I mean, you're going to hit some practical limitations just because to execute the simultaneous fracturing of the zipper frac, your wellheads do have to be close enough together to where you can get wireline, your crane to each wellhead, and your pressure pumping to each wellhead. But it really just kind of depends on the size of the pad, how many wells you have there. But it's not uncommon for an operator to say, just to use some good clean round numbers, let's say that they fracture each stage 4 hours, and it takes them 2 hours to run wireline. So what they would do, ideally, there in that case, they would have 3 different wells. Here, let me pull up a whiteboard here. Maybe I can draw this a little bit better than just explaining it. All right. So you'll have to excuse my artistic ability because it's not very good to begin with, and it's way worse if I'm using digital here. But so what I'm talking about, we've got 3 different horizontal wells. And we have, so it takes 2 hours. Yeah, this is really bad with the digital for the wireline run. And it takes 4 hours per stage to frac. So ideally, it would be a 3 well scenario because now you could fracture this well for 4 hours, run wireline on this well for 2 hours, and then move it to this well really quickly for 2 hours as well. So that way your wireline is constantly running while you're fracturing. So that's a really simple example there, but it kind of depends on just overall how your wellheads are distributed, how your wells are distributed all together, or wellheads, frac jobs, frac time, all that good stuff. So if you have, some operators go in where they have multiple wellheads really close together, and these wells they'll drill this direction, these wells they'll drill this one. So these wellheads may be very, very tight together. So in that case, you may could do 10 at a time. It may require more than one wireline unit, but there's not necessarily a set how many wells can you do at a time. It's going to be very application dependent.
Okay, thank you. Now the last question for today is what is the average lateral length and the number of stages per well and the average number of clusters per stage?
So it's always difficult to really do averages, just because even within one country, there's a lot of different variances. So I'll kind of give you an estimate based on U.S. wells. So if you look at U.S. wells, the average lateral length is somewhere between 8,000 to 10,000 feet. But you have outliers as well. Some wells up to 15,000 feet or even higher. So and then you had a couple of operators that were publicly stating before the pandemic anyway that they were going to attempt some 20,000 foot laterals. The current record in the U.S. right now is in the Permian, and it's 17,800 feet, somewhere in there. And then there's also one in the Utica that's 17,600 feet or something like that. So there are some extended laterals out there, but generally speaking, 8,000 to 10,000 feet is kind of the average. And once again, that's going to be very place specific. You go into some plays in Canada, the Canadian side of the Bakken, the Viking, the Cardium, In a lot of cases, those are anywhere from 4,000 to 6,000 feet long. So it's going to be very dependent on everything, basically. The number of clusters, so I covered that a little bit, but currently the average number of clusters is about 6 to 12 per stage. And the number of stages is where it kind of gets tricky and difficult to keep up with, because some of the operators that were running, let's just use good clean round numbers. If they were running 50 stages with 3 clusters per stage, now they may be using 25 stages with 6 clusters per stage. So the stage count it's shifted higher and it's shifted lower at the same time. Higher because of the longer laterals, lower because of the additional clusters per stage. So it's kind of all over the board. If I had to try to guess on average stages or stage count in the U.S., I would say probably anywhere from 30 to 50 is the average in most cases. But once again, it just depends. You've got your outliers. If you Google NCS Multistage and Kicking Horse, they had a 225 individual stage with sleeves in 2018, I believe. So stage completion also has some case histories with over 100 stages. So there's a lot of different exceptions to that rule, or to that average.
Okay, thank you. I want to highlight that this session has been recorded and it will be uploaded soon on PyPatrick's YouTube channel. And also for those who are considering to join this course, they already missed a quiz. However, they can still join, yet they should pass the 3 remaining quizzes and do the final exam. Now, for those who already joined since lecture 1, please continue doing the quizzes, and also don't forget to do the final exam. And the link for the Google Classroom for this course are posted on the Arab Oil and Gas Academy Facebook group. And now, best of luck. That's all for today. Thank you again, Engineer Burton, and have a nice day, and see you in future webinars. Thank you.
Thank you. You too.